Moving right along in the integration world, partial fractions. Don't mix up the word partial fractions with integration by parts. This is what we're focusing on today, and the obligatory warning. That's enough. Let's move on. So now partial fractions, integration by partial fractions, is going to involve problems that look very juicy in the factoring world. So first of all, you're probably always going to see these in fractional form. And when it looks like the denominator will factor very easily, you should consider partial fractions. So they're going to be pretty easy to identify. And you see some mysterious steps here on paper. Ignore those for a second because I want to put your brain in the right frame of mind to receive that information. Okay, to receive that information, transport yourself back to Algebra 1 or Algebra 2 when you had to add these two together. And this is when the teacher first broke the news to you that when you need common denominators, it isn't always as easy as something like, hey, what's 2/3 plus 7/8? You became good at finding that common denominator. All of a sudden you had to find a common denominator in a situation like this. It's deceivingly simple. You would just say, hey, both of these need to be represented in my denominator. That's no big deal. Now you didn't necessarily know what the numerator was, but then you figured it out. You said, hey, to go from here to here, I multiplied the denominator by x minus 2, so that numerator got multiplied by x minus 2. Here to here, I multiplied by x plus 7. The numerator multiplies by x plus 7. And you kind of know you're correct when you do this, because you would have to continue on with this problem, but if you wanted to, you could say, hey, those cancel. Hey, those cancel. And notice this over this is where I started. This over this is where I started. But this is the type of idea that's going to be happening in your integration by partial fractions. So let's head back up there. I'm going to unzoom here a little bit. All right. I identify it as a prime candidate for partial fractions, and I go ahead and factor. We'd love if it was given to us in factored form, but it's not. Now from here I say, you know what? This looks like it could have been the result or the common denominator of an addition problem that looked like this. If I had this in a denominator of one term and this in a denominator of the other, I would end up with that. Now I don't necessarily know what would have went up here or what would have gone up here, but I know this. Some mystery number here and some mystery number here will make this equivalent to that. So this is kind of a reverse application of that common denominator thing I was talking about. I get this, I rewrite it like that. That's your first step in partial fractions. Now we're going to do kind of a unusual step. Notice that what I have here is an equation. By the way, I'm no longer in the integral. Notice the integral is not being written over here. I'm just working with the integrand and I'm doing some trickery. Integrand, boom. Then what the heck happened here? Well, if I view this as one huge equation and I multiply through both sides by x plus 5, x plus 4. Now remember, when I multiply an equation by something, it has to go to all terms. Well, when I do that, this cancels with that. When this multiplies by this term, the x plus 5's cancel, leaving a times x plus 4. This times this term, the x plus 4, numerator, denominator, numerator, numerator. So using that algebra technique, I now get this. You got to wonder why we're doing this, but it's going to all become evident. All right, so now at that point, I have a new equation I'm working with, and I'm going to do this kind of like an algebra trick. Different people probably have different ways of getting this done, so here's what I do. In this equation, I want to find out what could my A and what could my B represent, or what's their number value. So I do this thing. If I plugged in an x equals -4, this term goes away because it's a times negative 4 plus 4, a times 0. So if I plug in a negative 4 here and here as well, what I get is negative 4 minus 3, that's my left-hand side, equals a times negative 4 plus 4 plus b negative 4 plus 5. Okay, that looks like a mess, but notice that this turns out to be a 0. This is negative 7, and this is b times a positive 1. What I've found out that is this: when x equals negative 4, b equals negative 7. Nice. Now when x equals negative 5, and I chose this negative 5 because I know it's going to do some shenanigans over here. When I plug in a negative 5, I get a negative 5 minus 3, and then a negative 5 plus 4, and a negative 5 over here, negative 5 plus 5. Okay, what I end up with here is a times negative 1 equals negative 8. Remember, this part ended up being b times 0, so it went away. So if negative a equals negative 8, a equals positive 8. All right, so I had basically some algebra trickery to find out what a value for a and b might be. Wait a second. If I have an 8 and a negative 7 up here, that means that would be equivalent to this. And this is the thing that's inside my integral. So watch what we're going to do with that. Taking this statement up here, which is really equivalent to the integrand, I say, let's integrate that statement that's equivalent to the integrand. I did all sorts of algebra trickery to come up with this. All that algebra trickery gave me something in a different form that's still equivalent to that. Now, why would I do that? I think you see that. This antiderivative is very easy. It might not look that way, but remember this. Anytime, oops, you can't see that over there. Let's do a side note with a different color. Anytime I have the integral of something and the denominator has an exponent of 1, that's a 1, the antiderivative is the natural log, plus c, of course. If my exponent was not a 1, then I'd have some version of reverse power rule, but when the exponent is 1, it's natural log. Well, check this out. This is an x plus 5 to the first power. This is an x plus 4 to the first power. So that makes for a really easy antiderivative. A really easy antiderivative. A couple of things to be aware of. When that b was negative 7, it's still plus a negative 7, plus a negative 7, but then I wrote plus a negative as just negative. Don't forget the plus c. And then the picky thing that the natural log, x plus 5 and x plus 4, those technically need to be in absolute value bars because the natural log function will not accept negative inputs. You, of course, know the natural log function. It looks like that, and it does not live in any negative x domain. All right, that's a pretty clunky technique, but it's a technique that you can get right every single time. You just have to practice these steps, become familiar with them, and hopefully understand that there's an algebraic reason behind everything that you're doing. So it's not really just a set of mystery steps, it's a set of mysterious algebra steps. That is your integration via partial fractions. I know you can get literally every single partial fractions question correct. You just need to make sure you practice so you feel comfortable with the technique. See ya!